Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 22 and we will continue from where we left in the previous lecture, and that is basically the comprehensive threshold voltage modeling for low temperature. So we have already learned that there will be also in our previous lecture, if you remember, we were looking into the fact that my intrinsic carrier concentration will reduce because of band gap widening and others. Let's look at the third case, and this third case is basically increase in bulk potential, right? Bulk Fermi potential. Bulk Fermi potential primarily means that the Fermi potential in the bulk of the device, not at the silicon dioxide interface. So if you have a device which is available here, and this is your oxide layer at this particular point, and then you have this metal layer here, then this is my interface, right? Silicon dioxide interface. I am saying the bulk at this particular point at very low values, or as you go deep inside the bulk where you do not have any surface phenomena coming into picture. Now in this case, if you know the Fermi bulk potential, it is given as kT by Q ln of Na over Ni, right. Now if you look very carefully in this formula, it consists of two parts which is temperature dependent. One is of course this part directly temperature dependent, and we discussed with you just now Ni is also temperature dependent. What has happened is, as you lower this capital T or temperature, this quantity reduces, right, but this quantity actually also reduces, and therefore this whole quantity actually starts to increase. So there are two competing phenomena. One is kT by Q, also referred to in many of the research papers or at places as UT or thermal equivalent voltage, and is 25 millivolts at 300 Kelvin multiplied by natural log of Na by Ni. With decrease in the value of Ni, Na by Ni increases, natural log of that value increases. So these two are competing factors, but overall what happens therefore is that phi f obviously now becomes a strong function of temperature. Now in order to satisfy the charge neutrality in case of a completely ionized Na, right, at 4.2 Kelvin, if you remember, P of P, number of holes in P type semiconductor, is given as Ni exponential, right, phi f, right, but divided by ut. What is phi f? Phi f is this quantity divided by ut. So it gets cancelled out, exponential natural log of Na by Ni is there. This is approximately equals to Na, acceptor ion concentration. Now Ef needs to lie very close to the valence band edge for the very fact that this is a p type semiconductor. So Ef will lie very close to valence band, right. And why should it lie? Because it should need to compensate for Ni, no. You see what has happened is, as you lower the temperature, your Ni has actually reduced, it has gone down. In order to compensate for that, because charge neutrality cannot be sacrificed, in order to do that, this goes down. As it starts to go down, it tries to take the electron from the valence band up to the Fermi level, right, Ef, which is phi f star actually. Right. The increase in the phi f, the change is of the order of generally of the order of 0.1 volt to approximately 0.5 volt, depending upon the value of Na which you have. So if you draw the graph of two things, that this is my temperature axis, which is log scale, and this is my phi f, which is the Fermi potential, and phi f star, change in the Fermi potential but the change in temperature. Now if you look at the solid phi f dashed lines and solid lines, you will see that as the acceptor ion concentration becomes larger and larger, the change in the phi f becomes smaller and smaller. So this is for this, then this is for this. This is for say 10 to the power 18 number of acceptor ions, this is 10 to the power minus 17 number of acceptor ions. So this difference is just from at t equals to 0 is this much, this is the value of difference, whereas for this the value of difference is this much. So difference goes on increasing as the value of the Na goes on increasing. I will explain to you why this happens. As the acceptor ion concentration becomes more and more, the modified Fermi potential has to be moving down more closer to the valence band edge in order to compensate for the increased value of the acceptor ion, right. And that is the reason you have less bending, which primarily means it goes slightly below it, right. This is the case when you have exactly the same nature. Now you please understand this important point, that you will have the freeze out, when there are no carriers available, when your Fermi potential is exactly equals to your star equals to your phi a, which means that acceptor ion energy level and the modified Fermi level, if they exactly match with each other, you will have a carrier freeze out or partial carrier freeze out will be available to you. So, this you need to keep in mind while we move forward in this case. So, this is one important point, which means that the increase in the value of phi f, right, the Fermi level potential, the increase in the value, which is basically given by ut ln of Na by Ni, this increase in the value of phi f because of decrement in the value of Ni affects the threshold voltage adversely, right, and this causes the increase in the value of the threshold voltage. Now, however, phi f increase is not very strong or not very prominent. Over the energy scale, if you look at the energy scale, it will hardly few millivolts or milli electron volts change is expected at that particular point, right. Now, at around 4.2 Kelvin, where you are actually putting your electronics, all the electronics into system, the silicon body which you are doing will be actually degenerate in nature. The degenerate we have already discussed in our previous slide, that degenerate basically means minus phi f, right, should be approximately 3 kT, which means that Eg by 2 is half the band gap minus the Fermi. So, basically if this is my Ec and this is my Ev here, this is my Eg by 2, this is my Eg by 2 here, right, this is Eg by 2, and if the Fermi level is very close to the Eg by 2 level. So, this is my Eg by 2 layer, and if you subtract the Fermi potential from the Eg by 2 value, it should be at least less than 3, right, it should be less than 3 kT. 3 kT is the value of the amount of energy which we are looking into. If this condition is fulfilled, we define this to be as the degenerate semiconductor. Therefore, there is an increase in the bulk Fermi potential, phi f increases, Vt actually goes up, and the silicon which is actually kept in the bulk becomes degenerate in nature. Let us come to the third point, is basically my incomplete, this is the fourth point, sorry, incomplete ionization. Now, if you take phi f star, the changed value of the Fermi potential at 4.2 Kelvin, this will be comprising of two terms. One is ut kT by q ln of Na over Ni with the minus sign ut ln of 1 plus square root of 1 plus 4 alpha Na divided by Ni, and this divided by 2. This is referred to as phi f, and this is delta phi f, change in the Fermi. So, this is the initial value of phi f, and delta phi f is the change in the Fermi potential, right. Alpha is, do not worry about it, it's a slightly complicated in formula, but at least for the completeness sake, we define this to be as exponential acceptor ion concentration minus intrinsic carrier concentration divided by kT, right, and basically these are the formulas. G is the occupancy which you will see here. If you look at this equation here, then the first term is primarily the bulk Fermi potential, and this is the change in the Fermi potential because of threshold voltage change, band gap widening, and so on and so forth. Now, as the acceptor ion concentration becomes larger and larger, and this is very important, this Na value starts to increase. I am talking about p-type semiconductor, right. This increase basically means that this whole quantity actually becomes larger and larger as Na becomes larger. As a result, the difference between phi f and the revised new value phi f star becomes actually lower and lower. So, this value goes on increasing, and therefore, the difference actually starts to reduce, and at very high value of Na, they might be almost equal to each other, thereby making my phi f star almost equals to 0. This is what I called initially as sort of an incomplete or almost freeze out condition which you see, right. So, these are the few basic concepts which you should be aware of as far as incomplete ionization is concerned. Now, with this background which is happening to you, let me now come to the final part of the discussion, and that is development of an analytical threshold voltage model, right. So, this is basically we developing an analytical threshold voltage model. Now, and this is basic physics again, we try to match it, right. So, I know that my gate to bulk voltage will be given as psi s plus phi ms plus epsilon silicon epsilon s into psi s is a function of psi s upon Cox, where this is basically my surface potential, and epsilon silicon is my permittivity, silicon permittivity. This is silicon permittivity which you see, and epsilon s is basically, which is the epsilon s is basically my electric field. Let me write it as Es, it is easier to explain. This is electric field, and this electric field will depend upon the surface potential here. What is the surface potential? Surface potential is nothing but the potential at the silicon dioxide interface, right, and it varies as you move from source to drain. Now, since surface potential will vary as you move from source to drain, the electric field which you find out will be a function obviously of the psi s, and that is the reason you see I am writing at epsilon silicon into Es by Cox, right, that gives you the potential, and this Es, this electric field, is again a function of psi s. Psi s is the surface potential in this case, right. And for this phi ms is the work function difference between metal and semiconductor, is phi m minus phi s, work function difference. This is the work function difference between metal and semiconductor. At this stage, we are not taking into consideration any fixed oxide charges or interface trap charges. We are assuming that they are not available in this, and therefore, they are not coming into the threshold voltage equation. Now, the threshold voltage is usually defined as gate to bulk voltage for a given surface potential psi s, and therefore, we define that when the surface potentials becomes equal to the inversion surface potential, then at the number of electrons will be equals to Na minus. When this condition is reached, that the number of electrons in a p-type semiconductor, if I am inverting it, is exactly equals to Na minus, we define that the threshold voltage has been reached. Now, let us go one by one the temperature dependency, and let us look at the surface potential dependency at a cryo. So, if you are working at 298 or 300 Kelvin, the inversion threshold voltage is taken to be equals to, if you remember, 2 phi f, and you know the reason why, because it has to become now as much n type as it was initially p type. So, that is the reason you have to bend the band at least twice the Fermi potential, and that is the reason you get a dip in the value. Now, the way we write down psi s bar is equals to ut ln of Na by Ni plus phi f star, which is the change because of low temperature, plus the channel potential, which is function of x. X is 0 at the source end and x equals to L at the drain end. So, x equals to 0 at source and x equals to L at drain. And if you look at V channel will be approximately equals to 0. So, VCH at 0 will be equals to 0 approximately, and VCH at L will be equals to approximately equals to VDD. I am not considering built-in voltage till now in this case. Plus, there will be another term known as VSB, source to bulk is there. Now, we need to evaluate the threshold voltage at x equals to 0 at the channel, and we will assume that source to bulk is approximately equals to 0. So, VSB will be equals to 0, and we are trying to find out the threshold voltage at source, right. That is what we are trying to do. Now, the threshold voltage which you will get will be given by psi s is equals to phi f, right, this quantity phi f plus phi f star, which you see here, and this will be approximately equals to 2 phi f star plus delta phi f, right, and this will be also referred to as 2 phi f minus delta phi f, right, and that is from here you can get it. So, finally, what we get is that my psi s star or psi s dash is approximately equals to 2 phi f minus delta phi f. Why 2 phi f minus delta phi f? You need to understand this point physically. 2 phi f is the amount of potential required to invert the channel, but because of band gap widening and stuff like that, other second order effect which is specific to cryogenic temperature, your potential, surface potential, is to drop by a factor of extra delta phi f, which is coming by virtue of the change in the value of Ni, widening of the band gap, and so on and so forth. And that is the reason it is not 2 phi f now, it is 2 phi f plus delta phi f. So, further bending of the band will take place in this case at 300 Kelvin. Now, if you go back further, if you go back, let me rub this portion because I do not have any free space as such. So, let me just erase all ink on the slide, and then let us start again the discussion which we are seeing. Now, let us come to the electric field. Now, the electric field, I am taking it directly from the paper. Electric field, which is a function of the value of the surface potential is given by ut by ld. It looks complicated, but it is actually not in a sense. Minus del phi f by ut plus ln of f of theta plus ln of 1 plus 1 plus alpha e to the power minus phi f by kt, and this will be in square root, which so VCH equals to VSB equals to 0. So, my VSB has been taken to be 0 in this case. So, this is the electric field. LD is a Debye length, and f theta is an empirical constant which is depending on other factors, natural log of f theta, let us suppose, and this also depends upon the value of temperature. All these are temperature. So, ut is kT by q, we already know about this. The two log term, natural log terms have some error, approximately 1% error is there in the natural log term. And finally, what you get from all these discussion is that the threshold voltage equals to 2 phi f minus del phi f plus VSB plus phi m star minus phi f star plus some function alpha multiplied by 2 phi f VSB. This gives you the final sort of a intermediate final value of the threshold voltage at low temperature, right. That gives you typically a good value of threshold voltage. Now, if you look very carefully in this expression here, as the temperature goes on changing, let us assume that my VSB equals to 0, my source and bulk have been grounded. So, this goes to 0, right. This is my metal work function, which is almost constant independent of temperature, does not play a role. What plays a role here is, again, this is 0, assuming to be equals to twice phi f. What therefore plays a role is basically this difference and phi f star. This difference is again a function of temperature, this function is temperature, and that is the reason Vt is a strong function of temperature whenever you are trying to design cryogenic low temperature design, right. Now, I will not go into the threshold into this thing, but if you plot now, if you plot temperature, right, and in kelvins, and if you plot delta threshold voltage change, which is basically, what does it mean? Del Vt is given as Vt minus Vt at 300 Kelvin, right. So, threshold voltage at any temperature T minus the original value of threshold voltage at 300 Kelvin. The difference between the two is delta Vt. So, at 0 Kelvin it has some value, and as it goes down, this actually starts to become like this. This happens at 300 Kelvin. This is approximately at 4 Kelvin. This is 0 Kelvin. This is temperature scale which we are seeing. So, I am assuming here Cox to be equals to 50 millifarad per meter square. Acceptor ion concentrations are 10 to the power 18 per centimeter cube, and I am assuming VSB to be equals to 0 in this case. And W by L ratios have been taken to be approximately 3 micron meter by 1 micrometer, right. So, it is a large channel device, and as the temperature goes on increasing, the value of the delta Vt goes on decreasing, which means that the change which you see in the threshold voltage is maximum at the cryogenic temperature, and it is almost 0 at the room temperature. And that is the takeaway from all these discussion, that the error in calculating the threshold voltage analytically or even mathematically, physically also, will be highest when your temperature is lowest, or when the temperature is almost near 4 Kelvin. And that is more so the motivation for studying such a course, that this course helps you to evaluate or understand what amount of error must be there, and therefore, a priori, if you can take certain measures to check for that change in the threshold voltage to be accommodated somewhere in the model, right. So, this study was not done to a larger extent earlier, because there was no requirement direct per se to go to cryogenics except for space applications where the temperature goes down to a bare minimum. But after this advent of quantum computing and the area of cryoelectronics came into picture, this study became quite interesting and important as well, as far as this course was concerned. Now, with this knowledge, let me now quickly understand the physics. Let us just go one by one, and this we have already read, but I have highlighted it for your, you can just stop your video and have a look into what it is written here. As I have discussed with you, as the temperature decreases, the energy band in the substrate of a bulk silicon ferro field effect transistor shifts, Obviously, as I discussed to you, EF has to adjust to maintain neutrality. I have already told you that, and therefore there is a Fermi-Dirac distribution scaling. The Fermi-Dirac distribution doesn't remain the same; it scales down, right? And EF will move much closer to the valence band edge at lower temperature. Again, I have discussed with you, which means that the difference between the Fermi level will be much larger. There will be requirement of more band bending. As a result, the threshold voltage will increase and eventually it will saturate, right? Similarly, charge neutrality model will assume that complete ionization of bulk dopant, but that's not true when your temperature goes down to a very low value, and therefore there's an incomplete dopant ionization available to you, and that is known as a freeze out. As I discussed with you, in freeze out conditions, charge neutrality is achieved earlier, right? So basically at T equals to 300 Kelvin, when there is no freeze out, you require lower band bending, and therefore you require much heavier charge neutrality at freeze out conditions. I told you about incomplete ionization, and then the reverse trend of there will be less band bending when the inverted charge carrier in the channel when incomplete dopant ionization is considered. When you consider an incomplete dopant ionization, you will require a less amount of band bending. Threshold voltage will vary, and the error in the threshold voltage will be much, or the difference in the threshold voltage will be much larger at 0 Kelvin or around 4 Kelvin as compared to 300 Kelvin. We have discussed this point. Let's finish off with basic numerical approach. So what is written here is that you need to calculate the position of the Fermi level in n types silicon at 110 K with respect to the intrinsic Fermi level, and the doping concentrations are given as this much, right? Nd equals to 2 into 10 to the power 18, and experimentally we are given these values of Ni at 300 and 211 K and 77 K. Boltzmann constant is also given. This is small k. So we can use the relation that EFI is basically the intrinsic Fermi level minus the actual Fermi level is kT, ln of P0 by P Ni. Ni is the intrinsic carrier concentration, P0 is the number of holes available. And if I assume that 100% ionization has taken place, then 2 into 10 to the power 18 value will be there. And then we get the value of this thing to be this much. Now let's calculate the value of EFI minus EF. You can find out that at EFI at 300 Kelvin, I get 0.4993, so this much. Then at 200 Kelvin is this much, which means the difference between intrinsic Fermi level and Fermi level increases, which means that the Fermi level is pushed downwards more towards the p-type semiconductor. That's the reason the difference goes on increasing. And at 77 K, it's largest, it almost becomes Eg by 2. You getting my point? At 77 K and below, it almost becomes equals to Eg by 2, because why it has been shifted down to the Fermi level position, right? So with these discussions, let me recapitulate what we did this lecture especially. We looked into the various aspects. We took this from a research paper. I will give you the details of the research paper in the next class, or maybe if you can drop me a mail, I will send you the details. But we did a basic idea about a comprehensive threshold voltage model, at cryogenic temperatures. We also looked into various models which are available for cryogenic temperature to understand this threshold voltage model. And then finally, we ended up using a simple numerical to showcase what we taught to you, that the Fermi level will shift more towards the acceptor level as the temperature decreases, is been showcased by a numerical problem at the end of the lecture. So with that, let me finish this lecture. I hope you enjoyed the lecture. Thanks a lot. We will meet once again in the next lecture. Thank you.